One of the most revolutionary things we learned in the 20th century was that time is not absolute. The rate at which time passes is different depending on how fast you're moving and how much you're accelerating. In particular, time passes slower the more you're moving. This fact has been confirmed experimentally countless times. Fast-moving muons take longer to decay, light emitted from a moving source has a lower frequency, and so on. But relativity of time can at first glance seem somewhat contradictory. Suppose we're flying past each other. From my perspective, it seems like you're moving, and so time should go more slowly for you, and from your perspective, it seems like I'm moving, so time should go more slowly for me. It seems crazy that we can both think time is going slower for the other person. Someone's time must actually be slower, right? Well, no. Take a look at my giraffe. It's 3 meters tall, and your giraffe is also 3 meters tall, according to you. But you're rotated relative to me, so you only measure my giraffe to be 2 meters high. And I'm rotated relative to you, so I only measure your giraffe to be 2 meters high. So we each think the other is measuring height distances as longer, but it's not a contradiction. It's just that we've rotated height and width relative to each other. And similarly, when you change your speed, you rotate the direction of time. I have another whole video explaining why, but it looks like this. If every passing second I move to the left, then my clock will tick like this. And if every passing second you move to the right, then your clock will tick like this. So when 3 seconds have passed on my clock, I'll measure only 2 seconds have passed for you. And yet when 3 seconds have passed on your clock, you'll measure only 2 seconds having passed for me. So we each think the other is measuring distances in time as shorter, but it's not a contradiction. It's just how time behaves when it's rotated. It affects not just the passage of time, but also our notion of the same time. However, there's still an unanswered question. What if I stay on Earth and you go off into space at high speed and then come back? Will one of us have actually aged more, or will we both have aged the same amount, despite constantly thinking the other was aging less? This conundrum is called the twins paradox, and I'll explain the solution to it in my next video. But in the meanwhile, can you use rotating time to figure out why the twins paradox isn't a paradox? Hey, Henry here. Thanks for watching, and I'd like to thank Audible.com for supporting this video. As you've probably heard, Audible is a leading provider of audiobooks, including fiction, nonfiction, and periodicals. If you're into physics, as I imagine you might be if you watch my videos, I definitely recommend checking out The Perfect Theory by Pedro Ferreira about how researchers like Einstein and others came to our modern understanding of gravity, space, time, black holes, and so on. You can check out The Perfect Theory or another book of your choice for free with a free 30-day trial at audible.com/minutephysics. Again, that's audible.com/minutephysics.